So let's start. So we're going to talk about acid-base titration today and then redox titration. So this is just a continuation of the topic that we have started 2 weeks ago, which is about titrimetry or titration. So as we have started titration 2 weeks ago, we said they are very important tools in providing qualitative and quantitative data for a sample. And they said to best understand titrations and the information they provide, it's necessary to understand what gives rise to the type or shape of the typical titration curve. Okay, so this morning we're going to tackle about acid-base titration. So if we're talking about acid-base titration, that means the reaction is between an acid and a base. Okay, so this is not new to you. You did a titration curve in your Gen Chem 1 if you took it to base. If I'm not mistaken, that's experiment 5 where you titrate your vinegar with NaOH, which you standardize with your KHP. In your Gen Chem 2, you do two titrations there at least for acid and base, one that is monoprotic acid, and the other one is a polyprotic acids wherein you determine the phosphoric acid content in your soda. Okay? And the topic of acid-base titration was also taken way back in Gen Chem 2 in the part of acid-base chapter. So there are two chapters there, acid-base and acid-base equilibria. So when you have a titration curve, usually you have what? The volume of the titrant that you add versus the pH. Okay? So usually you have a titrant there, which is a strong acid or strong base. Okay? And you titrated it with either weak acid or strong acid. So if you have a weak base as your titrant, you have an acid as your analyte. And whenever you do this, you will have a calibration curve. So typically the titration curve. So the titration curve would look like this. And then you can always say that the one in the middle here, that's your equivalence point. That's the part where your acids and base are of equal moles. Okay. And this morning, we're going to look at the different types of acid-base titration. So it just something to do with the strength of the acids or the base that being what we call titrate. So the way that we look at this is the typical titration setup. So you have here the titrant. So it can be an acid or a base. So whatever you have here, the other one should be the opposite. So if you have an acid as your titrant, your base is your analyte. If you have base as your titrant, your acid is your analyte. You cannot have an acid here and an acid here because that's not an acid-base titration. Okay? So if you're going to recall your Gen Chem, there are at least 4 types of titration, but on of which 3 is the only one that we have discussed. So one that has the strong acid versus a strong base, one wherein we have a weak acid versus a strong base, and another one where we have a strong acid with a weak base. Now you seldom see a titration where you have a weak acid and a weak base. So usually the first 3 are the typical acid-base titration. And you'll be able to identify what type of titration they are based on their titration curve. So if you have a strong acid, strong base, usually it's like this. And the middle that you have there is pH 7. or you can do it the other way around like this one, but still, okay, the equivalence point that you have there is equals to 7. Now, what happened if you titrate weak acid versus strong base? So I'm going to make the roll call now. Okay? What do you think is the equivalence point? If you're titrating a strong acid or a weak acid versus strong base, okay? What do you think is the equivalence point? Anyone? Anyone? Will it be equals to pH 7, more than pH 7, or less than pH 7? Okay? So someone answered there, pH 5. Anyone? So this is what? It's weak acid and strong base. So this is typically the type of questions that's being asked in multiple choice. Okay? So if we go, if you are asked, let's say, identify which pH or which titration curve represent a titration between a weak acid and a strong base. So usually you will have it like this one. Okay, so that's the 7. The other one would be like this. So it would be like that. So if you have a weak acid being titrated with a strong base, usually your pH is more than 7. Okay, so if you're going to look at it, it might be like this one. So your equivalence point would be above 7. Okay, and if it's a strong acid versus weak base, it is below 7. So the titration curve alone is enough for you to identify what are the strength of the acids or base being titrated. Okay, now let's try to do a titration between a strong base and a strong acid. So usually, if we going to look at this type of titration, all we need to do is monitor the amount of H plus or OH minus in a given solution. And they are the one that will dictate what the pH of your solution will be. So the reaction that we have, if we have a strong acid reacting with strong base, so we have H plus from strong acid, hydroxide ion from strong base to give you H2O. And if you're going to recall, okay, the K for this one is 1 times 10 to the 14. Now you may ask, why is it 1 times 10 to the 14? Because you all know when you have water, it dissociates to give you H plus and OH minus, and that's 1 times 10 to the negative 14. But what we did in the reaction here is we reverse it. Okay? So the way that we're going to determine them is based on the amount of the H plus and the OH minus that we have. And we could say we always have 3 regions whenever we do titration. At equivalence point, before equivalence point, and after equivalence point. But we can start, or we can at least add another region that we have here. Before titration. Okay? So, just like what we have learned from last meeting, the first thing that we do if ever we have a titration problem is determine the what? What the first step that we did last time in the titration problem? Anyone? The first step that we do is determine the equivalence point or the volume that is equal to the equivalence point. And in this thing, we can just use the C1B1 equals to C2B2. So in this problem, you will titrate 50 ml of 0.02 molar KOH with 0.1 molar HBr. Now my question is, which is the titrant and which is the analyte? You can answer it in the chat. So what is the titrant and what is the analyte based on the given system there? Anyone? What is the titrant and what is the analyte between HBr and KOH? Okay. So if we're going to look at here, the one whose volume is not changing, that is your analyte. Okay. So your analyte here would be your KOH. The one that is going to change in volume, that is your titrant, because that's the one that you're adding. So if we have a titration curve for that, this is the volume of your acid, and that is your pH. And what do you think happened here to the pH as you add more titrant? Anyone? So what happened to the pH as I add more analyte, as I add more acid here in the titration? Will the pH be the same? Will it go up? It will go down? Put your answer in the chat because that will be our quiz. Okay? So the pH decrease. So what will happen? It will be like that. Now, going back, so the first thing that we ask you to do is to do the determine the equivalence point. So what we do here is we have a C1 B1 equals to C2 B2. So this could be your acid, this could be your base. So if you're going to look at it, it will be moles of acid equals to the moles of the base. So based on this one, so you have 0.1 molar of HBr, you don't know the equivalence point, equals to 50 ml of 0.02 molar KOH. And by doing the calculation here, you're going to have 10 ml of your HBr at equivalence point. So at 10 ml of 0.1, that is equivalent or has the same number of moles as 50 ml of 0.02 molar of KOH. Okay. Now, if you're going to ask the question here, what is the initial pH? What is your answer? What is the initial pH of the solution? Anyone? My chat will be my record book for your quiz. So what would be the pH? Yep, but exactly what would be the pH? Anyone can give me exactly what's the pH is? Okay, it's 12. 12.3. Okay? Because initially, what do you have? It's all the base. So all you need to do is get the pOH of this and then get the pH, and that is equals to 12.3. So if we're going to look at it, we could say the start of the thing here, that's 12.30. Okay? And then when you keep adding the acid, okay, what do you think the region before equivalence point? Or what does this 10 ml represents? Anyone? Your 10 ml represents what? That's the volume wherein you have the pH at equivalence point. So what do you think is the pH at equivalence point for this? Is it 7, greater than 7, or less than 7? Anyone? What would be the pH at equivalence point for this reaction? To those who have not answered yet, okay? So the pH for this is 7. So what does it mean? Anything that is before at equivalence point is a volume that is less than 10 ml. So 10 ml is just like our boundary. Okay? So if your volume is less than 7, you are at the region before equivalence point. If the volume of your acid is more than 10, okay, you have a pH that what we call, you are at the equivalence point after the equivalence point region. So again, if your volume is 10 ml, the pH would be around 7. If it's less than 10 ml, so you expect the pH to be what? More than 7. If it's more than 10 ml, so you expect the pH to be less than 7. So let's look now at the region. Okay? So the first thing that I think have here is after we start adding the acid. So we look there at the region before equivalence. So you are add here, you are asked here. So what will be the pH when 3 ml of HBr has been added? If you solve it using GenChem, all you need to do is what? You determine the moles of the acid and the moles of the base, right? So mole of the acid would be equals to what? 3 over 1000 ml per liter. And then what's the molarity that we have there? 0.1. Now for the other one, it is what? Is it 50 divided by 1000? And then you have 0.02 molar. So if you're going to look at the calculation here, 3 divided by 1000 times 0.1. And then 50 divided by 1000 times 0.02. So I have this one. So which one will remain in excess? The acid or the base? After you add 3 ml of the acid. Okay, so you have the base. And if you're going to look at this, the reaction that happened here, so 1 times 10 to the negative 3, 3 times 10 to the negative 4. So all of this will be utilized. And the one that remains is 1 times 10 to the negative 3 minus 3 times 10 to the negative 4, which is 7 times 10 to the negative 4. And then you divide it with the total volume. So this is moles. So the total volume that you have then will be what? 3 plus 50. And then you divide it by 1,000. So you have there the corresponding molarity of your hydroxide. So 7 exponent negative 4 divided by 3 plus 50, or 53 divided by 1,000. What do you get? What concentration of the hydroxide remains there? Anyone? So what do you get when you do this calculation that you have here? So if I did that calculation, I end up with 0.0132. So I did this using knowledge that I should have learned from Gen Chem 2. But if we're going to do it following the way that we did it using the precipitation titration last week, this is how it's going to look like. So we look at the fraction of the hydroxide that remains. So 10 is the equivalence point volume. We use 3. So that means we have 7 over 10 fraction. And then we multiply it with the molarity of our base. And then we multiply it with the volume of the base over the total volume. And look what we get. Is 0.0132. So convince yourself that you can do it this way or this one. Now, we're not done yet, because if we're asked for the pH, what we have so far here is just the hydroxide concentration. So to get the pH, we need to convert first the OH minus to H plus. So we have the Kw divided by the concentration in hydroxide. So you have here the H plus. And if we're going to get the pH, we just get the negative log of this. So we have a pH of 12.12. Now, does this value make sense? Does this make sense? Where do we start? Okay. At the beginning, we have what? At the beginning, we have 12.36. 12.3 as written here. Okay, not 36, 12.30. So as you add 3 ml of your acid, the pH went down to 12.12. So question. Question.
Uh,
Now,
where,
okay.
where did you get this 7 times 10 to the negative 4 that you circled top right corner?
I subtract this value with this one.
Okay, got it. Yeah, all right.
Question. Now the next question that you have here is, what's the pH at equivalence point? And since this is a strong acid and a strong base, okay, the answer to that is usually this. Now, the next question that you're going to be asked is, what is the pH after equivalence point? Now, we can solve this before I show you how to solve it at 221 level. We can solve it as 112 level. And again, what do? Moles of the H plus and moles of the hydroxide. Okay? And the amount that we have here is around 10.50. So how do we look at it in terms of the moles of the acids and the moles of the base? So we know the moles of the hydroxides to be 1 times 10 to the negative 3. So all we need to do is determine the moles of the H plus. So you have there 10.5 over 1,000, so ml per liter, and then you multiply it with its corresponding molarity, which is 0.1. So this is just equals to what? 10.50 divided by 1,000 times 0.1. So that's 1.05 times 10 to the negative 3. So as you could see now, you have your H plus as in excess. How much of that? Okay, so you subtract this value with this one. So 1.05 times 10 to the negative 3 minus 1 exponent negative 3. So you have there 5 times 10 to the negative 5. And all you need to do is divide it with the total volume, which in this case is 10.5 plus 50. So 10.5 plus 50 will give you what? 60.5. And convert it to liters. So I get here around 8.26 times 10 to the negative 4. Which will lead me to what pH? Anyone? What is the equivalent pH for that? For those who have not answered anything yet. What's the corresponding pH for that value? Is it 7? Okay. So if you're going to get the pH of that, this is just what? pH equals to negative log of that number. So that's 3.08. Okay. So as I've told you, this is the Gen Chem level. Now, if we go to the 221 level, you can do it like this. Now, this time, you're going to look it from the perspective of the H plus. Why? Because they are the one now in excess. So you have the initial concentration. Now, you may ask yourself, why 0.5? Why is this 0.5 here? Anybody? Okay. Is it 0.5 because we have what? 10.5 minus 10. So this is the equivalence point volume. So you have 10.5. So that means you have an excess of 0.5 ml of your acid. And then you divide it with the total volume of the solution. And from that, you get this. So since this is already the H plus, you're able to get this as 3.08. So this is how you solve a strong base, strong acid titration problem. And if you're going to plot it, this is how it looks like. If you're going to have the first derivative, I think the way that you do is like this. If it's the second derivative, if I'm not mistaken, it will be like that one, passing through the zero. So that is the easy one. And usually I don't give questions like that in the exam, especially now when the exam is take home. Okay? The one that I usually do is the more challenging one, wherein one of the component is weak. Okay? So for instance here, we have a weak acid reacting with a strong base. So the question I would like to ask here, what do you think is the pH at equivalence point? Okay? What do you think is the pH at equivalence point? Those who have not answered yet. The pH should be what? Okay? So since the one that is strong is the base, so you expect the pH to be greater than 7. So if we're going to look at a specific example here, so there's a titration of 50 ml of 0.02 molar MES, which has a pKa of 6.27 with zero point 0.1 molar NaOH. So MES, there is, we can say an acronym of this acid. So MES means the morpholino ethane sulfonic acid. Okay. So the next question that I'll ask you here, what is the titrant and what is the analyte? So for those who have not answered yet, please answer that. What is the titrant here and what is the analyte? And how would you uh, how would the titration curve looks like? So I'm giving opportunities to those who have not answered yet. Okay. So the titrant there is your NaOH. Now, how would the titration curve looks like? So what do you think the pH? Is the pH the same all throughout, increasing or decreasing? Anyone? Okay. So in this case, the pH is increasing because you're adding a base. So you're going to see here a pH like this. And maybe the 7 would be around here. So the equivalence point is above 7. Okay. So we're going to look at this. So we have what? As usual, the three regions, equivalence point, before and after. And we can also put here start or before titration. So what is the pH before titration? Anyone? Before we even started the titration, what would be the pH? So if you recall your weak acid, so we could say we have it like this. So you have their 0.02 molar. You don't have anything. And then you have what? Plus x here, plus x, and this was minus x. So you end up with 10 to the 6.27 equals to x squared over 0.02 minus x. I think 10 to the negative 6.27. So I think I'm right there. So what would be the x here? The x is your H plus, and once you have it, you can get the pH. So I would say maybe close to this one, -4. And if I'm going to get the pH for that, that would be around 3.98. Or no, it's at 1.04, it's 1.03. And it's not even 3.98, it's 3.99. So that's the thing that I get. So that's the pH before the addition of base. It's just a typical weak acid problem, weak acid solution. Okay? So let's start now at the first region, the one before equivalence point. But before we do that, we need to determine what is BE. Anyone can solve for the BE? What's the volume at equivalence point here? I think it is the same values as our previous problem. So I don't know if everyone will agree that's 10 ml. 50 times 0.02 divided by 0.1. And I think I have a schedule thing there. So if you're going to look at the reaction, we don't have an H plus here. What we have is an HA because this is what? Strong acid. This is weak acid. So weak acid reacting with the hydroxide to produce an A minus and water. And the equivalence volume that we have there is 10 ml. So what does it mean? So we can have it like this. So this is a 10 ml. So this is at equivalence point. This is before. And this is after. Okay. So let's see how the reaction at this region before the equivalence point. So before any bases are added, that's the one that we have solved earlier, the one we end up with 3.99. So after we start adding, so that's the region before equivalence point. So before we reach the equivalence point volume, the behavior of the system is similar to a buffer. So if the behavior of the reaction is similar to the buffer, what equation are we going to use? Anyone? Okay. We're going to use, what do you call that equation that you wrote, Hanbo? Okay. What do you mean, no idea? Anyone, what do you call that equation? I'm going to send you back to Gen Chem. What do you call that equation? Here, no idea still? Okay. It's the Henderson-Hasselbalch equation. Oh, God. Going to be a disaster in your final exam if all of them are multiple choice. Okay, it's the Henderson-Hasselbalch equation. So the way that you look at this, you have pH equals to pKa plus log of A minus over HA. So all you need to do is monitor this. So after you add 30% of your equivalence point volume, or we could say 3 ml of the base. So what happened? You can write it like this. So you have 3 over 10. And then why is this 7 over 10? Anyone? Okay. So remember, the equivalence volume is 10. So when you add a base, okay, so the 10 ml there, that is your what? If we're going to plot it, it is HA plus OH minus to give you H plus water. So we could say 10 ml, 10 equivalents for you to reach the equivalence point. And you add what? 3. So what happened to this? Okay. At the end, you subtract this one with 3, you subtract this with 3, and you form plus 3 here. So this will become 7, none, and this become 3. And remember, we are looking at H plus and HA. Okay? Or we could say this is what? Your A minus. No, this is not an H plus. This should be an A minus. So that's an HA, and this is an A minus plus water. That's my mistake there. So if you're going to look at this, so this is your A minus, that's 3, and this is your HA. Now, since they have the same volume, okay, the way that you look at this, at the end, you utilize 3 out of 10 of the A minus, and then here there's 7 out of 10 from the original one. Or you can just put there 3 here and 7 here, because if you're going to look at this 10 over 10, they will just cancel out. So this is the important thing that you need to know here. And once you get that, you add it with the pKa and you end up with 5.9. Now the question, does this value make sense? Anyone? So when you added 3 ml of the base, all of them are used up. There's no excess of the base. What it do is just convert some of your HA into A minus. Now, does this value make sense, anyone? 5.9? So you started with what? 3.99, you add on a base, it becomes 5.90. So it makes sense because the pH increases. Okay? Now, before we go to the equivalence point, what happened if we add 50% of the equivalence point? So when that happened, so the 3 over 10 and 7 over 10 here will just become 5 over 10, which is also 1/2. And 1/2 over 1/2 here will give you what? 1. And log of 1 is equals to what? Anyone? What is log of 1 equals to? Okay, equals to 0. So if that is equals to 0 here, so your pH is just equals to pKa. So that is equals to 6.7. And again, does this make sense? Does this value make sense? Okay, yes, because by this time you already add 5 ml. At 3 ml, it's 5.9. At 5 ml, it's 6.20. Now, let's go at the equivalence point. As we said, it should be higher than 7. It's not equals to 7. So how are we going to calculate the pH at equivalence point? So I don't know if you recall this reaction. So at equivalence point, what will happen? You don't have any more HA. All of the HA is converted to A minus plus water. Now what will happen to this? It will behave like a salt. Okay? So when it behaves like a salt, this reaction is reversed. So when this reaction is reversed, you have this. And since you have a hydroxide there, you're going to determine the Kb. And remember, the one that is given is Ka, the pKa. So at this point, you're going to determine the hydroxide concentration to get the H plus, which will give you the pH. Okay? So what does it be? So if we're going to continue the thing, we look at what's the concentration that we have here now. So initially that's 0.02. Okay? But since this is already at equivalence point, so we could say the initial volume of your weak acid divided by the total volume of the system, which is now 60. So you look at the contribution that he has there, so from 0.02 times 50 over 60, you end up with this one. So that's the one that you're going to use here. And what will happen? So you have here 0.0167, and then you have x, and then you have minus x, plus x, plus x. So you end up with x, 0.0167 minus x. And you have here the Kb, so you end up with x times x over 0.0167 minus x. Now you may ask, why Kb? Anyone? Why did we use Kb? To those who have no answer yet. Why did we have Kb? What's the clue that we need Kb and not Ka? Because Ka is the one that's given. Okay? Because we have hydroxide in the product. So if we're going to get the corresponding value of Kb, this is what we have. And we set it up here. So if we're going to get for the x, this is the value that we got. And again, this is hydroxide concentration. And to get the H plus, so we have 1 times 10 to the negative 14 divided by 1.76 times 10 to the negative 5, you get the negative log, you get the 9.25. So what can you say? Does the value make sense? Is 925 greater than 7? So if you're going to do the plot, so the value that we have there is not really in the middle, but around, we could say in the middle here, but 7 would be around here. And that's around 9.25. Okay? So that's at equivalence point. So now you see the point why I prefer to give this one, weak acid versus strong base, compared to strong acid versus strong base. Because if a strong acid and a strong base titration, automatically your equivalence point is equals to 7. But that's not the case here. So the way that it do, you allow the reaction to complete, and then after that, it will hydrolyze. Because A minus is a conjugate base of a weak acid. So now we have equivalence point. What happened after equivalence point? So everything is just based on the excess hydroxide. All you need to do is determine how much of your hydroxide remain unreacted, divide it with the total volume. So you have the hydroxide there, convert it to H plus, and you end up with the pH. So if you have 10.10 ml added there, so only 10 is needed to you at the equivalence point. So you have there an excess of 0.1. I think there's some mistakes here. This should be 10.10. Okay. And you end up with this. And again, this is hydroxide. And if you're going to get the pH is equals to 10.22. Okay? So if we summarize what we have right now, this is how it looks like. Okay, the calculated titration curve for the reaction of 50 ml 0.02 molar of morpholino ethane sulfonic acid with 0.1 molar NaOH. So this is initial pH, and then before equivalence point wherein it acts like a buffer, and then the equivalence point, and then after equivalence point. So as you could see there, the equivalence point, that's the steepest part of the curve. So if we summarize what really happened during that time, so at the initial point, it's the reaction of the weak acid. So just getting the pH using the weak acid, which most of you were able to do in your exam last week. And then before equivalence point, you have the buffer region. So all you need to do is know the Henderson-Hasselbalch equation. And then at equivalence point, it's like a hydrolysis reaction. So you complete the reaction, and then you react. You allow your conjugate base to undergo hydrolysis, which in this case produce the hydroxide. And then in the excess OH, or after equivalence point, it's the behavior of your excess hydroxide. Now, if we're going to do it the other way around, wherein you have a weak base being titrated with strong acid, this is how it works. Initial point is the behavior of the weak base. Before the equivalence point, it acts as a buffer. At equivalence point, the same thing, hydrolysis. Okay, but this time, it's the conjugate acid of a base. And after equivalence point, it's the excess H plus. That's the one that will monitor the uh, or govern the pH of the given solution. So if you have a strong acid-base titration curve, this is how it looks like. The equivalence point is exactly around 7. pH equals to 7. Okay? And if you're going to look at the features of the strong acids and strong base titration curve, the pH starts out low, which reflects the high hydronium concentration of the strong acid and then increases gradually as the acid is neutralized by the added base. So suddenly the pH rises steeply, and this occurs in the immediate vicinity of the equivalence point. For this type of titration, the pH is equals to 7. So if you're going to look at here, it, it rises slowly, and then all of a sudden it just rises up. So beyond the steep portion, the pH would increase slowly as more base is added. Okay? So if you want to work on it, I leave this up to you. Strong acid and a strong base titration curve. So this is the way that we solved earlier, that one I told you about Gen Chem level. So all you need to do here is get the moles of the HCl, okay, and compare it with the moles of the base. So 40 and 0.1, and then you have 20 and 0.1. Which do you think is in excess? Anyone? We're not going to answer it, but I've just asked this question to give the chance for the others who have not answered yet. So 40 ml and 0.1, so we could say H plus is the one in excess. So that's the one that will what we call the shots, or the one that is responsible for the pH. Now the second region that we have here at the equivalence point when 40 ml of the NaOH is added, so this is what we have. So the pH that we have here will just be equals to 7 because everything is used up. And after equivalence point, so you added what? 50 ml. So you have an excess of 10 ml of your NaOH. So if you're going to look at this, so this is the hydroxide. So you end up with this moles, and then you divide it with the total volume, which is in this case 50 over, or 50 plus 40, 90 ml, and convert it to liters. So you should be able to get the concentration of your hydroxide. Now for the weak acid strong base titration curve like this one, so this is how it looks like. So see the difference here? If it's a strong acid strong base, you started here. But since it is a weak acid strong base, you started a little bit higher. And as I have told you before, equivalence point, they behave like a buffer. That's why we put the thing here, buffer region. So if you're going to look at the four major difference between strong acid strong base titration curve and a weak acid strong base titration curve, one of them is initial pH being higher in weak acid strong base titration curve. Number two, there's a gradual rising portion of the curve. It's called the buffer region, and it appears before the steep rise to the equivalence point. And then number three, the pH of the equivalence point is greater than 7, as you could see here. The pH is around here. If you look at the weak acid, weak base is around here. But if it's a strong acid, strong base, but if it's a weak acid and a strong base, it's much higher. So that's another difference that they have. And then the steep rise interval is less pronounced. So it's not really as steep as the one that you have here in a strong acid. strong base. And then again, these are the type of questions in your multiple choice in the final exam or in the third exam. Now the last one that we have, the weak acid and strong, weak base and strong acid titration curve. So this is the same thing. It's just like how do you call this? The flip side mirror image. So if you have it like this, in the strong weak acid strong base, in the other one weak base strong acid, it will be like this one. And if you're going to look at the difference, the initial pH would be what? 7, more above 7, because you have base initially. And then you see a gradual decreasing portion that's called the buffer region before a steep fall on the equivalence point. And the pH at the equivalence point is less than 7. And then after that, when the pH will decrease slowly as strong acid is being added. You can also have a titration curve like this one. And you observed this when you did your Gen Chem 2. So as you could see here, okay, you have sulfurous acid, which is weak acid, titrated with a strong base. So you have here this. So you have a buffer region, and then the pH at equivalence, first equivalence point, and then you go another buffer region, and then you get to the equivalence point. So we could say this is what? Ka1, and this is Ka2. And if you're going to look at the features of this type of titration, you could say the loss of each mole of H plus shows up a separate equivalent point, but only if the two pKa's are separated by 3 pKa units. So what does this mean? So if we're going to look at this, this is 1.85 and this is 7.19. So you can only see it because it's more than 3 pKa unit. But what do you think happen if it's less than 3? Anyone? Hello? What do you think happen if there is less than 3 pKa units between the two pKa? Will the equivalence point more pronounced or less pronounced? Can you say I'm here? Can you put in the chat box that you're there? Because it seems like I'm talking to myself here. Okay. So if you have less than 3 pKa, most likely it will be like this one. You're not going to see them. So if it's like this, you will just have, so it's not more pronounced. Okay. So if you have an equivalent titration curve, so what happens if you have 3 pKa, like phosphoric acid? So how are you going to look at it? So maybe it will be like, if you have 3 pKa, so maybe it's like this. But usually you could see that if the difference here is less than 3, you cannot what we call see it distinctly. Okay, so the pH at the midpoint of the buffer region is equals to the pKa of the acid species, and the same volume of added base is required to remove each mole of the H plus. Okay, so how do we look at this titration curve? What happened if we have a titration curve like this one? How are we going to conclude in this first figure? What can we say here? The stronger the acid, what can you say about the equivalence point? Anyone? Anyone, especially those who have not answered yet? Because my chat will be my record. Okay? Is it equivalence point is lower? What can you say about the equivalence point the stronger the acid is? Look at this. So the strong acid has this from here going here. The weakest acid would just have it here. Why this is the weakest acid? Because that's the one that has the lowest Ka. What's the term that we use here? Can we say the stronger the acid, the wider is the region for the equivalence point? Or I think the right term there is steep. Compare it with what we call the pH4, pKa4. So the region of the pKa4 is from here going here. pKa2 is from here to here. So the weaker the acid, the less steeper is the equivalence point. Now, how about the second one here? What can you say about this? How is the steep of the equivalence point affected? So these are weak acid. So what can you say about this? The higher the concentration of your HA, the what? The steeper is the equivalence point, because again, so you could see 20 millimolar, the black one, compare it with the 2 millimolar, which is this one.
So would the one in the middle with 0.002 millimoles HA, would that be the weakest acid?
No, here, in terms of the weakest, no, this is not the weakest acid. This is something to do with the concentration.
Okay.
So the lower the concentration of your weak acid there, the less steep the equivalence point. So it's hard to determine the equivalence point. So that's what this figure is all about. Here, the stronger the acid, the steeper is the equivalence point. Here, the more concentrated your weak acid, okay, the steeper is the equivalence point. Now, the last part of the acid-base titration has something to do with its indicator. So why phenolphthalein becomes pink when you keep adding hydroxide ion? Okay, so usually if you have indicators, what they do is they just change composition, which resulted to change in color. So for instance, the thymol blue that we have here. So if you're going to look at the different structure of your thymol blue, so this is how the thymol blue look like at low pH. And this is how your thymol blue looks like at high pH. So you could say, why is this at low pH? Because everything is protonated. Why this is at high pH? Because everything is deprotonated. So as you could see here, it has 2 pKa values. So if you have 2 pKa values, that means you have 3 forms. And fortunately, those 3 forms have different colors. Okay. So at low pH, it is red. Now, if you're going to remove some of the proton, the proton here to become this one, after passing to the second, the first pKa value, the red becomes yellow. And if you keep adding base there, removing the H that you have here, so you're going to form this chemical structure which give you a blue color. So it's all about removing and adding hydrogen. Okay. And we can also observe this one if we have phenolphthalein. So if it is at a pH less than 8, wherein all of this area that I encircle is protonated, you have a colorless phenolphthalein. But if you're going to add hydroxide ion, so what's the hydroxide ion do? Will abstract the hydrogen that you have here. So it becomes deprotonated here. It will become pink. So we could say the transition that we have here is between 8.0 and 9.6. Below 8, it's colorless. Above 9.6, it's pink. That's why, what is your experience with phenolphthalein? A drop could make a large difference from a colorless, or we could say light pink. You add the drop, it becomes dark pink. Okay. And there's also another form of phenolphthalein, and this is when you put it in a sulfuric acid. So as you could see here, there's 2 hydrogen present, but in the presence of sulfuric acid, you have to have 3 hydrogen that is present there, and your colorless solution can become orange red in terms of phenolphthalein. Okay. Or if you're going to make it very basic, when you remove everything there, so here as you could see, there's still what? A ketoenol form that you have here. Okay. So once you make it very basic, your phenolphthalein can go back to being acidic, what we call colorless. So everything just depends on the color. That's why I'm not sure if you have heard or read it when they use this so-called purple cabbage. at different pH, what happened? They have different color. Because cabbage, they're being plant or natural in nature, they contains a lot of these so-called anthocyanins. So at different pH, they exist at different color because they have different form. So the other thing that you can look at this is bronchosol green and bronchosol purple. So if you're going to look at the transition range that you have here, so this is blue, this is yellow. So the equivalence point is 5.54. So you can only use an indicator when, okay, you're looking for the pH near the transition point. So I'll ask you, can you use your phenolphthalein when the pH that you're looking for is between 3 to 5? Yes or no? Okay. How about the others? Can you use phenolphthalein when the pH transition is 3 to 5? Okay. So the answer is no. Why? Because it will always remain what color at 3 to 5? It will always remain what? Pink or colorless at pH 3 to pH 5. So at pH 3 to pH 5, it will always remain colorless. Okay. Now, this is your guide of what indicator you're going to use. And this will be helpful in your next exam. Because you might be given a question where you are asked, what is the appropriate indicator for a pH range equal to, let's say, 3 to 5 that I gave you? What will be your answer? Can I use methyl orange? Yes or no?
No.
It's between 3 to 5, okay? So what does it mean? Lower than 3, it's another color. Higher than 5, it's another color. Or lower than 4 is another color. Higher than 5, it's another color. So if you're going to look at this methyl orange, okay, it has a transition range between 3.1 and 4.4. So it can be used. Okay. Congo red, can we use it at 3 to 5 transition?
Yes.
The answer is yes. Thymol blue, can we use it at 3 to 5?
No.
Okay, the answer is no. Okay, why? Because it will remain the same color. It will, what color will it be? If we're monitoring the pH transition between 3 to 5, your thymol blue will always be what color? Anyone? So those are the type of questions that you're going to be asked, and please don't email me what table do you mean. So this is what it means. Okay, so this is just to determine if you know what you're going to do. It's just like a practical thing. So you are asked, you need to measure this pH. What's the indicator that you're going to use? Okay. And if you want to look a much easier way for comparison, this is how it looks like. So here right away, you can determine what indicator you need to use at a particular acid-base transition. So as you could see here, Phenolphthalein is only applicable, it's between 8 to 10. You cannot use it at 5 to 6 because it's all colorless. Okay? You cannot also use, we could say, crystal violet to determine transition at high pH. So question before we take a break and then continue on with the redox titration. Question? So let's have a 5-minute break, okay? Okay, there's a question. Okay. So 5-minute break before we continue redox titration. So let us continue. This one with redox titration. So this was the experiment that was performed last week. And if we're going to look at the redox titration, it's basically main on oxidation reduction reaction between the analyte and the titrant. So there are many common analytes that you can find in chemistry, biology, environmental and material science that can be measured by redox titration. Okay. And the way that we look at this is we measure the reduction oxidation potential. And from that, we can be able to determine a complex reaction by analyzing them, and in some aspect, enzyme mechanism. Okay. So the way that we have the redox titration curve is we look at the voltage change as a function of the added titrant. So those who did the experiment, this is how it looks like. Your burette contains your cerium ion, and your analyte contains your iron ion. So if you're going to look at the reaction, you have here your Ce4 plus and your Fe2 plus reacting to produce Ce3 plus and Fe3 plus. Now my question is, which is the oxidizing agent and which is the reducing agent? Anyone? Because we say it's a redox reaction, so that means there's an oxidation agent and there's an reducing agent, oxidizing agent and reducing agent. So which is which? Which one is oxidized and which one is reduced?
I think the cesium is oxidized and the iron is reduced.
Okay. So
wait, it might be the other way around. I think it's the other way around.
So before we go with electrochemistry next week, because electrochemistry is just about redox potential, so we're going to do it now. So what happened to your Ce4 plus? Was it oxidized or reduced? Ce4 plus. So what it is, oxidized or reduced? We do it one by one, okay? So Ce4 plus reduced as one of your classmates type. How about the Fe2 plus? This was what? Oxidize. Okay. Now, the next question. What is the role of your Ce4 plus? Is it your oxidizing agent or your reducing agent? Okay. So your Ce4 plus is your oxidizing agent. So that makes this the reducing agent. Very good. So my students should always know this meaning here. So Leora means loose electron, which means it's oxidized and it acts as a reducing agent. Geroa means gain electron. It is reduced and it's the oxidizing agent. This is oxidized because this becomes more positive. It becomes more positive because it loses electron. This is reduced because it becomes more negative because it accepts or gains electron. Okay? So stuff like that you should have learned in the Gen Chem. But until this time, you're still confused. So I hope this at least cement this concept that when you lose electron, you undergo oxidation and you are the reducing agent. That when you gain electron, you undergo reduction and you are the oxidizing agent. Now, this reaction has a large K value. Okay? But if you're going to look at the reaction that we have here, what usually is formed? We are not after the formation of a precipitate. We are not after the change in the color. What we're after is in the change in the potential. Okay? So if you're going to look at the hap reaction that is happening, this is what you will see. The two systems that you have. Now, what have you learned from your Gen Chem 2? Both of them are what? What reaction do we have here? Both of them are what type of reaction? Is it a reduction reaction or an oxidation reaction? Anyone? So what type of reaction is this one? So this is a reduction reaction. So based on your reduction potential, if you have two reduction reaction, the one that has the lower potential will undergo oxidation. So between the two, this is a higher reduction potential. So this remove what we call remain in the reduction reaction form, while this one, which is lower, it undergo oxidation. So this become Fe2 plus, producing Fe3 plus an electron. So canceling out the electron, giving you this overall reaction. Okay? So what does the shape looks like? For those who did the experiment, this is what it should look like. And just like any typical titration, again, we have three regions. Before, at, and after the equivalence point. Okay? So for those who attended last week, this is what you observed. The four students who was in the lab last week. So if you're going to look at the before the equivalence point, whenever you add a Ce4 plus, you create an equal number of moles of Ce3 plus and Fe3 plus. Because what happened? Every time you add some of this, okay, both of them are converted to form this and this one. And you have excess Fe3 2 plus that remains in the solution. Okay? So the amount of your Fe2 plus and Fe3 plus are known, and from that you can use it to determine the cell voltage. Now the thing is, you don't know how much of the unreacted Ce4 plus remain. That's what we call the residual amount. And if you're going to look at the reaction there before the equivalence point, so we could say we can use the iron half reaction relative to the calomel reference electrode, this one. And the way that we look at it, the potential that we have there is the potential of the indicator electrode, which is the positive sign, minus the potential of the reference electrode. So the way that we do it is we just use this one, Nern's equation. So E equals to the reduction potential, the standard, minus 0.0596 log of Fe2 plus that you have this one, which is your product, over the reactant, minus 0.241, which is the potential of your reference electrode. And if you're going to simplify it, this is the value that you will get. Because I think in your lab report, you have to do some calculations like this. And I didn't include that in the pre-lab discussion because I know that we're going to meet in the lecture to discuss about this. Okay? Now, as we continue, we can look at some special point like this one. 1/2 of the equivalence volume. So you may ask, what is the equivalence volume here? Again, you have the C1B1 equals to C2B2, but you have to take into consideration the moles, right? So the moles of Ce4 plus and the moles of Fe2 plus. At least this is a 1:1 mole ratio in terms of the reaction. So we use a simple one because we can have a complicated one like the experiment that you did 2 weeks ago, the one with the Mn4 and the oxalate. Okay. So at this volume, what can we say? At 1/2 of the equivalence point, we're going to have the same concentration of Fe3 plus and Fe2 plus. So this will become what? 1. And log of 1 will give you 0. So you end up having this amount because this one will all become 0. So 0.526. Okay. So the point in which the volume is equals to 1/2 of the equivalence volume is analogous to the point in which the pH is equals to pKa in an acid-base titration. And another special point that we have here is before we start the titration. Okay, when Ce4 is equals to 0. So voltage, you cannot calculate it. The concentration of Fe3 plus is unknown because all you have there is what? Fe2 plus. Okay, so if Fe3 plus is 0, you could say your voltage is a negative infinity. So must be some Fe3 plus from impurity or Fe2 plus that is what we call oxidized. So voltage can never be lower than the value need to reduce the solvent. And you also have to consider this one, the water. And this has a potential equivalent to this. Okay? Another special point that you have here, this time we go in terms of the CE that is being added. So when you have a volume that is twice the equivalence point. So this is the time when you have the same concentration of your CE ion. So from that point, what happened is you end up with this value. The potential that you have there is 1.46 compared to the standard potential that is equals to 1.70. So I hope you see the difference between this and this one. So this is the standard potential, and usually it's listed. Now this one, it depends on the concentration that you have. So the point at which B equals to 2BE is analogous to the point at which the pH is equals to the pKa. So those are the one before the equivalence point, wherein you get the potential of each of the species that you have. What happened at the equivalence point? So in the equivalence point, you have enough Ce4 plus that you added to convert your Fe2 plus to Fe3 plus. So that means at this time, mostly it's all the products. And you have small amount of the reactant. Does that make sense? When you have the equivalence point, it's mostly products. The reactants are already what? A little bit low, or all of them are a little bit used up. But if you're going to look at the reaction, this is the reaction that you have. So your Ce3 plus is equals to your Fe3 plus, because those are the products. And your Ce4 plus is equals to your Fe2 plus, because these are both the reactants. So if you're going to combine the reaction at equilibrium, you end up as this one for Fe and this one for your Ce. Okay? And as you go on, you don't know the concentration I told you of your reactants. So you can solve either equation independently to determine the positive potential. So what you do is you add both equations together. So when you add them, what will happen? Let's look at your math knowledge. What happens if you add them? So you're going to add this, and then you're going to combine these two here. And you end up with this. So where did I get 2E? 2E plus, because I add these two. Where did I get 2.47? I add this. And then this one, since they have the same expression, all I did is just combine the ions in the numerator and the ions in the denominator. Okay? So if I'm going to do this, adding them together, so I have it here. So what happened here? Ce3 plus and Fe3 plus, which are both the products, are the same. Both the reactants are the same. So if they're both the same, most likely what will happen? This is just equals to 0, because that's log 1. So log of 1 is 0 times this one is 0. So 2E plus is equals to 2.47, and I divide both of them by 2. I have an E plus, that's 1.23. And if I'm going to use that number, subtract it with 2.241, this is the reference electrode, you have 0.99. So I asked those who did the experiment, what's the voltage that you got when you reach the equivalence point? The 4 students who did the experiment. Is that close to that?
No, it was really, really, really high.
Remember, the one that you use is MB, and this is B. If I'm not mistaken, some
Okay, yeah.
has around 800, the other has around 900. I think some get 1,000 MB. So that is just the same as 0.99 B. Right? So that's the equivalence point voltage, and it's independent of the concentration and volumes of your reactant. And I think when you keep adding, I think the change in the voltage after the equivalence point is not so high, because you already reached the equivalence point here. Okay, so that's how you get the equivalence point. So you get the difference between, or the way that we added here. So in the end, you get the positive electrode, which is 1.23 potential minus 0.241, which is your reference electrode. Now, how about after equivalence point? So what happened here? So this is just the opposite situation compared to before the equivalence point. So here you have equal number of moles of your products, and then you have now excess Ce4 plus, because you keep adding Ce4 plus, but you don't have any Fe2 plus anymore. Okay, so the amounts of your Ce3 3 plus and Ce4 plus are known, and you can use it to determine the cell voltage. So residual amount of Fe2 plus, because Fe2 plus is almost converted to Fe3 plus. So if you're going to look at this after the equivalence point, the one that you took into consideration is your Ce4 plus, which is equals to 1.70. And if you're going to do it like what we did earlier, so 1.70 minus 0.05916 log of the products over the reactant minus the calomel reference electrode of 0.241. And this is what we get. 1.46 minus 0.05916 log Ce3 plus and over Ce4 plus. So this is just based on Walter Nern's equation. And if we're going to continue, the titration now only depends on the ratio of the reactants. And it's independent on the concentration and the volume. So same curve if diluted or concentrated by a factor of 10. So if we're going to look at the shape of a redox titration curve, so we have here what? A symmetric titration curve. So this is a reaction stoichiometry that is not 1:1. And look what happened at the equivalence point. So if it's 1:1, it's usually in the middle. But here, it's around 2/3 the height for you to see the equivalence point. And this is a titration curve for 2:1 stoichiometry. So I think the way I look at this, the two here, two there, okay, is the reason why this is 2 over 3, because 2 plus 1 here will give you 3. Unlike if it's at the middle, so that's really a 1 is to 1. So 1 over 2, which is the total, that's 1 half. So if we're going to look at the system here, the one that we have is TL, tantalum. Okay, so we can use, in addition to electrodes, some indicators in redox titration. So they use peroin, which has an oxidized and reduced form that is different in color. So electrochemical measurements, we use at the current potential is the one that we use in the lab, can be used to determine the endpoint of a redox titration. But we also have redox indicator. So this is a chemical compounds that undergo color change as it goes from oxidized form to its reduced form. So the oxidized form of peroin is blue and the reduced form of peroin is red. Okay. So oxidized plus the number of electron giving you the reduced form. So if you're going to look at what happening during the redox indicator, I'm just showing you what's happening here. So there's a color change for a redox indicator that mostly occur over a certain range, okay, where the standard reduction potential is the standard reduction potential for the indicator, and n is the number of electrons involved in the reduction. So for instance, we have here peroin. So it has a standard reduction potential of 1.147. So the color change is relative to the standard hydrogen electrode. So from this, we end up this range. And relative to the SCE, that range will now become to this. After subtracting the lowest and the highest form with 0.24 which is the potential for your reference electrode. So I don't know if you could see the video, the drop of the thing there, how they change color. So it has their blue going red. Okay. And the way that you look at this reduction potential here with the other redox indicator, so this is what it has here, 1.25 compared to the other one here. So the way that it do is, in order to be useful in endpoint detection, a redox indicator range color should match the potential range expected at the end of the titration. So what does this mean? So if you're working at 1.25, okay, you use the one that has 1.25, just like in the pH indicator. So you cannot use penosapranin in this setup because it's 0.28. Okay. Maybe you can use the tris-bipirin ruthenium in here, 1.29, but the others you cannot use it at this equivalence point. And you have to take into consideration that you're subtracting this one, these values, with the saturated calomel electrode. Okay, so adjustment of analyte oxidation state. So I think we go back here to potassium permanganate. We can say that this is what? A self-indicator. Why do we call them a self? Why do we call KMNO4 a self-indicator? Anyone? Why did I say that KMNO4 is a self-indicator? Anyone? Uh-oh. Windy here. So we call it a self-indicator because what happened? It changes on its own. From red, it becomes what? Colorless. Okay? So the violet color that we have there, that's MnO4 minus. The colorless that we have there is Mn2 plus. But you know, there are other form of your MnO4, Mn thing. You can also have an MnO2. What charge do you have for MnO2? What is the charge of your Mn? What's the oxidation state of your Mn or oxidation number? So this is +2. This is, if I'm not mistaken, +7. So the Mn in MnO2 is plus what? Anyone? So if you recall your Gen Chem, this is Mn +4. And this one is Mn plus 6. Yeah. So different oxidation state, different color. Mn +7 is violet, Mn +2 is colorless, Mn +4 is brown, and Mn +6 is green. So that makes it a little bit versatile. Okay. And they use KMnO4 to titrate with the vanadate, vanadium, no, this is called the vanadate here. So before, near, and after equivalence point. So you have the blue, and then a green, and then a little bit of pink. Okay? And that ends our lecture on redox titration. We don't have any calculation for this one. The way that you're going to do calculation is in your laboratory. So question. We still have a lot of what we call time. So not all of you has answered in the discussion forum that I requested. So I think as of now, there's only 7. So I want all of you to say something on it. So we will have one more lecture that is next week. It's about electrochemistry. And then after that, you will have your third exam. And then after that, you will have your final exam. So we're going to look at the remaining days that you have. So what days today? This is already what? November, right? So November 2, and then November 9, and then November what? 16, and then November 23. So that's what we did today. And then you have electrochem next week, and then third exam, and then final exam. And then in the lab, we're only meeting what? November 4 and November 11. So we're going to do here experiment 10, and we're going to do here experiment 12. So my question, The original idea is your final exam is all multiple choice. Are you okay with that?
No.
How about the others? Where are the others? Hello? So are you okay that your final exam are all multiple choice? I want reply from the others. Because if Jalen's the only one who's not there, so she's the only one who will have a multiple choice and calculation, and everyone will have multiple choice. So where's the others? Of course, you will have enough time because I will give you the whole period for all you to do multiple choice. There is a reason why you're given less time for the multiple choice and less, we could say, grace period. Why I don't open it in a wide range of time.
But
You're
we
taking
have
it take home. That's why I want it less time. And how sure am I you're not talking with one another when you take the exam? And that's the reason why the window that I have for that is like from 10:30 until 12.
will we be able to backtrack, like go see other questions?
I think the last exam, I was able to do that. So most likely it will be like that. But the other thing that I'm going to offer to you, but I think you're not going to accept, is the use of respondus. But I don't think at this time you're going to be amenable to that. That's why there's always some compromise that I have. So the idea is what, 50 items, multiple choice, but after your second exam, the highest that I can get is 24 out of 30. So 8 out of 10. And then everything has a score that is teenager, which is
For the
not good
multiple
because
choice, I have a question. Is it possible that you can like put all the questions like to show up at once?
that's the thing. It can only happen if you're going to use respondus. There's always a compromise here.
Oh, okay.
I'm doing it in GenChem, but they're using respondus because you cannot have all that you can.
Mm.
There will if you're going to go for all for multiple choice, those simple calculations will end up there. That's why I'm giving you until next week. What do you want to be? You want an all multiple choice or you want the one that we have here? Because based on the time that we have, I can utilize the Wednesday that we don't meet to give you the calculation, or it's up to you if you want to go with the multiple choice first. Now you may ask what's the reason why I have to do like a multiple choice, because when you take this ACS exam or exit exam, all of them are based on the multiple choice. Because the thing, what I'm thinking is we can always utilize the lab time. Because as you know, we're open here. I can utilize that time. And you cannot tell me that you're going to do other stuff during that time because that times belong to our class. I can put the problem here and the multiple choice here. Because I still can go the same 50 points item in the multiple choice with some problem as my backup plan, just in case this is a disaster. You know what I mean? So I can always go to the backup plan to improve the score that you have if ever you have a disaster multiple choice exam. Although it may be additional work for me, it's fine. So the backup plan here, these are the one that's all calculations, covering everything. You have a week to think about it. And still, you still have a third exam in case you forgot. Okay. I can always prepare the what thing because I think last semester they went multiple choice, but every time I have the multiple choice, I have to give them additional exam that has a calculation. If it's a multiple choice, we're not going to cover the whole 3 hours, maybe at the most 2 hours, the typical exam that we have. You can do backtracking. That's the one that I can assure you. But I cannot have the all thing because without the responders, I'm not sure if you're communicating with one another during that time. So that's the compromise that I always put on whenever I give exam. Okay. So it's up to you. You have to decide by next week because I have to prepare the question. But I told you I'm okay. It's okay with me. If your multiple choice is okay, then we can get the multiple choice. If not, then we have to go and see if the backup plan will help you improve your score. Because this is the first time that I'm going to do this in this setup. Remember, when it's multiple choice, it's black or black and white. If you're wrong, you're wrong. There's no gray area. At least in the calculation, there's some gray area. Okay, you will always get something if you put something on it. And I don't know what will happen to us after tomorrow. Okay. I told you, typically the final exam of analytical chemistry is a multiple choice exam. That's why I'm trying to what we call get the feel of how the class performed. That's why I'm putting these alternatives that we have. The questions for the final exams are already ready because usually that's the one that is given every year because I don't return the final exam. You only have 2 days to decide after the third exam because the time that I'm allotting you is you take the exam on Monday for the third exam, and then we're going to utilize the what we call Wednesday lab as the time for the problem solving. Okay? Because what I want is after the exam on 23rd, I don't want to disturb you anymore. So if you have that problem solving exam on the 18th, I have something in me that I can use to improve your final exam your final exam grade. That's what it means there. Because 23rd, I think that is also the week of the Thanksgiving, right? So I don't want to disturb you during that time. By the 23rd, that's the last time that we're going to at least, we're not going to meet, but you have interaction with the class. So we might be going on, you have an exam on the 18th and you have an exam on the 23rd. Okay. So lab report will be due on the 18th because we're going to meet on the 11th as the last meeting. So for the lab, there are two experiments that is due this week. The both of them, the redox titration with the spectroscopy or use of absorbance last time for the nitrite. Okay? So I'm giving you a week to look at it, but I would say worst comes to worst, we do the 2 exams. I mean, it's my, we could say, insurance in case you don't do well in the exam, in the multiple choice exam. So that's I think that's the proposal that I'm giving to you. And the setup that we have is the same. I'm going to give you 3 hours. We're going to utilize the time, the Wednesday afternoon that we're supposed to be in the lab. So maybe I'll open it at 1:30. You have to submit it by 4:30. At least give me at least one lab this week. If ever you cannot finish it. Okay. So question before we end our session today. So if none, I hope you vote in the election tomorrow, or we have voted already earlier than that. So I hope we have a good mood for those who are going to perform on Wednesday. And I hope everything will be okay so we can also perform our last experiment next next week, Wednesday next week, because we don't know what will happen. Okay? We don't know what will happen because we have someone who's crazy enough